In this screencast, we continue our introduction to Quicksort. We're going to do an informal analysis motivating randomization of the algorithm, followed by a more careful analysis. And as we continue through Kaupo Gap, the clouds are clearing. So here's Quicksort and its helper procedure partition. Let's first look at what partition does here. We've got a constant amount of work pretty much everywhere except for we have a loop that grows with n because it iterates in proportion to the number of the elements in the array, which begins at p and ends at r, and this runs from p to r minus 1. So this is clearly theta of n. So looking at the main procedure itself, Quicksort, we're going to have that theta of n cost is paid here within each call to Quicksort, where it's a non-trivial size problem to solve. But the recurrence will of course depend on how the partition divides up these two arrays. So let's think of the worst case and the best case. Worst case is where the partition picks off only the pivot element itself, and then we have t of n will have to be called on the n-1 remaining elements. One of these calls will be on the n-1 remaining elements. The other call will be the one that doesn't do anything because p will be not less than r. It'll actually be 0 elements. And that last element of the n-1, of course, is the partition that was taken out. And then there's also the theta of n cost here for the partition that we have to pay. So that, of course, is equal to t of n-1 plus theta of n. And it's pretty easy to see that this is going to have to happen order of n-1 times, and each time will involve theta of n cost. And so this is your classic n squared. So the worst case of Quicksort is actually worse than insertion sort, which makes us wonder what's so quick about it, but we'll get to that. Now let's look at the best case. This is when the subarrays are completely balanced, when the pivot out of some range of values, the pivot that we chose that's sitting over here happens to split the remaining elements exactly in half because it's the median value of the elements in the array. That means that the subarrays always have about n over 2 elements. It's actually slightly less because we picked off that 1, so it's really about n-1 over 2, except actually 1's going to be ceiling and the other's going to be floor. But we're dealing with asymptotic analysis, so we don't have to worry about those details. We know the growth rate is about n over 2. So here we use the recurrence relation where we have 2 calls. Up here we had 2 calls as well, but we knew that one of them was going to be t of 0, so we didn't bother writing it in this other recurrence relation form that I'm going to use now. But here we have 2 calls of equal size, so we can say there's 2 of them and they are both t of n over 2 plus theta of n cost at each level. And if you look this up in the master theorem, or you just recognize this is, of course, is theta of n log n. And if you want the details on that, that's because f of n, which is theta of n, is actually theta of n log base 2 of 2, b and a. Of course, log base 2 of 2 is 1, so it's theta of n to the 1, which is the same as theta of n, so it falls into case 2. And case 2 says the solution is theta of n log base 2 of 2 log n. And this, of course, simplifies to just n, so it's n log n, giving us this. So that's the best case analysis. It's pretty efficient. Now there's further discussion in the textbook concerning what happens when we have something in between the worst case and the best case. Let's say 9 out of 10 times it does this thing up here. It just splits off one item. But only 1 out of 10 times it does this thing here, it splits it nicely in half. And they do an analysis to show that you still get n log n behavior, because as long as the ratio between the worst case splits and the best case splits is constant, that just changes the base of the log, but it's still logarithmic, and we know that bases of logs don't matter for asymptotic analysis. So check that out in the text if you want to see that argument. So it turns out that the best case is, by those more informal arguments, is closer to what we might expect. But if we look at what led to the worst case, this leads to a modification of the algorithm. What led to the worst case is our picking of an unfortunate pivot, right? Well, what do we do if our evil adversary comes along and says, I'm going to give you worst case data all the time, where the pivot always picks the element that is either the largest or the smallest, and so Quicksort, you can never know when it's going to run fast. How do we deal with that? Well, previously we dealt with that through randomization, through randomized algorithms. So let's see how we can randomize Quicksort. One question I meant to raise earlier is what would happen if Quicksort were given sorted data, either sorted in increasing order or sorted in decreasing order. That's something you might think about. Okay, let's look at the randomization strategy. Now, previously we dealt with the problematic data configurations by permuting the input data, randomization before you start the algorithm. That could be done. We could just use a regular quicksort and have some separate procedure that randomizes the data before sorting, but that's expensive to have that separate step. And it turns out we can actually do this naturally as part of the quicksort algorithm itself. There's a natural choice point here, where essentially rather than picking always the last element of the array here, we can pick, R is usually what our pivot is. Instead of just accepting what's there, we can sample randomly from the whole array what our R is going to be. Let's say, we do a random sample and we pick some other element there, and then we swap it. And then we can proceed with the regular quicksort algorithm using the last item as the pivot, because we've swapped it with a randomly chosen one. And that, of course, is what these two lines here do. It chooses some random position between P and R, inclusive. We should include the current R as one of the options, one of the candidates, and then exchange the R with the I chosen. That's what I showed here. And then proceed with the regular partitioning algorithm, which doesn't have to be changed. And so the randomized quicksort, of course, just calls this randomized partition, which is going to do the random pivot choice, and then call the regular one. And of course, the randomized quicksort has to recurse on itself, not on the other one. So this strategy of random sampling essentially gets the same effect as if we had randomly permuted all of the input data to ensure a random distribution of permutations of the keys. Now let's do an analysis of what this accomplishes. So we're climbing now from the upper valley of Kaupo Gap onto the floor of Haleakala crater, and it's getting rather late in the day. My notes and the textbook give a worst case analysis, a more detailed formal one, but I'm going to leave that out for brevity. It leads to the same result, theta of n squared. And another reason I'm leaving it out is we're really more interested in the average or expected case with randomized algorithms. Why? Well, randomization means that the worst case isn't very likely. That's the whole point. So we're going to do an analysis here that nicely demonstrates the use of indicator, random variables, and some useful strategies. So if we examine randomized quicksort, and these following comments apply to regular quicksort as well, there's very little real work done in the main procedure. It just does a test and it does some calls, one assignment. So the real work is done here, but that itself just does another test and a quick exchange, order of one, and then calls partition. So whether it's randomized or regular quicksort, the real work is done here in partition. Now, sorting algorithms are often analyzed in terms of comparisons, the number of comparisons made. So a good way to count the overall run of this loop, every run of this loop is going to have this comparison, regardless of whether the if succeeds or not. So we'd like to count the number of comparisons in each call to the partition, but we don't know the structure of the partition. We don't know the size of the partition. It's going to have different sizes depending on what the pivot was, and depending on how these p's and q minus 1 and q plus 1 and r broke down. So here's a general strategy for analysis. If it's hard to count things one way, such as locally, then count it another way, such as globally. So rather than try to count how many comparisons there are in a given call to partition or in each call considered separately, we're going to count the total number of comparisons across all calls to partition. So let's let x be the total number of comparisons in all calls to partition. Now to set this up, let's consider how many calls to partition there are. Well, each call to partition is going to return a position that gets passed back up and used here to compute the other partitions. The pivot is removed. It goes from p to q minus 1 and from q plus 1 to r. So every time partition is called, one element is removed from consideration. Therefore, a partition can be called at most n times. So the overall work done is going to be big O of n for those n times you set up and do the call to partition, plus the work to do the comparisons. So rather than writing a recurrence relation where we count the lines in here and write it recursively, we just say, let's kind of ignore the recursive structure. Let's just say across all calls, we know we got to do that much work here, the x is here, and then across all these calls here, eventually the real work ends up being down in here, and it can be counted by counting the number of comparisons right down here. So how do we do that? What is x? Okay, I've rearranged things a bit here. So first of all, for ease of analysis, we're going to call the elements A, z1, z2, zn, with z sub I being the ith smallest element. Notice that this is not the order in which they appear in the array. This is the order that they would be in after they're sorted. We're just giving the items names. Okay, now we're going to define a set, Zij, to be the set of elements between Zi and Zj inclusive. And we'll see how these are used later. So we want to count the number of comparisons. We can observe that each pair of elements is compared at most once, because the elements are compared only to the pivot element, and then the pivot is never used in any later call to partition. We want to count the number of comparisons, and we can note that each pair of elements is compared at most once, because elements are compared only to the pivot. That's the pivot, remember? And the pivot element is never in any later call to partition. So any two Zi and Zj will only be compared once. So now we bring in indicator random variables, which are those variables that take on value either 0 or 1 depending on whether an event happens. And as you may recall, they're very useful in summations because they let us count things up in easier ways. So the indicator random variable we need here is whether or not Z of I and Z of j is compared to each other. And as I've just argued, this will only happen once. So let's let the indicator random variable xij, where Z sub I is compared to Z sub j. So since each pair is compared at most once, the total number of comparisons, x, what we're looking for, is the sum of all of these possible pairs of comparisons. So we use summation from I is 1 to n minus 1, and then we'll get the nth element here. J is I plus 1 to n. This is a very common pattern. It's obviously picking all pairs, or hopefully obviously, picking all pairs out of a set of items, x, I, j. So essentially count up all the ones for which when Z of I was compared to Z of j. And now we work the expectation magic. Let's take the expected value of both sides of this equation Okay, now we apply the linearity of expectation to move the E in. And then here we apply lemma 5.1, which is the expected value of a random indicator random variable is the probability of the event. And this is a pattern you've seen several times before, setting up the thing that's easy to count, summing it up to be the thing you're interested in, taking the expected value of both sides of the equation, using linearity of expectation to move the expected value into the thing that you can count more easily, and then replacing it with its probability. Now previously we had already figured out the probability before we took these moves. At this point we haven't figured that out yet, so now we have to look at what's the probability of comparing z of I to z of j. So what is the probability of comparing zi to zj? Well, when it's hard to determine when something happens, another useful strategy in analysis is to rather think about when it does not happen, and that might clarify things. So let's say x is a pivot. The pivot is always compared to everything else in that call to partition. So the pivot, if the pivot is not z of I or z of j, it will be compared to them. So after that comparison, we never have to compare z of I and z of j to each other. Not only theoretically, because we already know their ordering, but because that's how the algorithm works. They will be put into two separate partitions. They'll be in two separate boxes on subsequent calls, and so they will never be compared to each other. So we only need to deal with a situation where one of them becomes the pivot item. So let's consider all of the items in Zij, and suppose either z of I or z of j is chosen as the pivot before any element in that set. Then that element as the pivot will be compared to all of the elements of Zij except itself. The probability that Zi is compared to Zj is the probability that either of them is the first element chosen. So this probability here will be the probability that Zi or Zj is the first pivot in this set of elements. But these are independent events, mutually exclusive events actually. If one is chosen in that set, then the other one won't be chosen. So we can sum the probability that Z of I is the first pivot chosen from Zij, Z of j is the first pivot chosen from Zij. So we just got to figure out what these numbers are. But Zij has j minus I plus 1 elements by its definition. So the probability that any one of those elements is chosen first is 1 over j minus I plus 1. So we can rewrite these probabilities here as follows. It's 1 over j minus I plus 1 for the first one being chosen, plus 1 over j minus I plus 1 for the second one being chosen, which is of course 2 over j minus I plus 1. So we now have a probability to substitute into the analysis. We're looking for this. We've got it now. We can substitute this up here and continue. Now we just have to simplify this. We've gotten rid of all the non-algebraic things on this side of the equation, except that I have to get rid of this equal sign here. So we just need to solve this summation. Well, there's an equation 8.7 in the back of the book for a harmonic series. This is a strategy you often take where you look up a formula that's sort of like what you have but not quite and figure out how to transform it. So we've got some small constant over a variable. Well, there's two variables and it's a different constant. And we're running not from 1 but from something other than 1 up to n. But if we're able to make it look like this formula, we would get natural log of n plus O of 1 would be the result. So we got to do something to make this equation apply to that. And we can do that by setting k will be equal to j minus 1. and then we're going to shift the summation indices down I. So instead of n, this is going to be n minus I, and this will be I plus 1 minus I, which will be 1. So k is going to run from 1 to n minus I, and then that will match this, where n minus I is playing the role of n over here. So let's rewrite that. That part stays the same, but here's where the change is. Well, getting closer. N minus I here can be n here, but we got a 2 instead of a 1, and we got a plus 1 instead of just k here. Well, we're doing big O analysis. You know, we can tolerate a little bit of sloppiness here. We can get rid of the plus 1 in the denominator by switching to inequality. And the 2 is just going to come out to be a constant item, which is going to drop out of the big O analysis as well. But we'll get to that later. Right now, let's do the inequality part. Oh, and also the inequality lets us just go ahead and run this up to n. Because, of course, if you add more terms, these are all positive elements, it's going to be bigger. So it's going to make that even simpler. So now this applies here. And here's where we get rid of the 2 just because we're going to replace it with big O of notation. So this whole thing is going to be just the outer summation, big O of this expression here, but natural log is just a different base than log base 2, and this is just a constant term, which doesn't grow as fast as the natural log. So we can just write this as big O of log base 2 of n, because that will be a similar a bound. It will be the same set of functions. And that, of course, because now here we're summing order of n of them, we're summing order of n log n's, we get the final result. So that is a more rigorous proof that the average running time of Quicksort and the expected running time of randomized Quicksort is n log n. We might emphasize that Quicksort is very efficient in practice whenever you're not giving it already sorted data. It has low constants, values, and it works in place. So it's always should be considered when you're sorting a large amount of data that's not in a nearly sorted order. If it's nearly sorted, use insertion sort. It's pretty fast on that. That concludes our introduction to Quicksort, and in particular in this screencast, the analysis of Quicksort, including randomization. And I did make it to Polycoo Cabin. I only had a few hours before sunset to get back down the 7 miles, so I just stopped here for 15 minutes at one of our most beloved spots on Earth and then headed back down.